Welcome. Today, we're going to be putting on our detective hats. We're diving into the world of coordinate geometry, where points on a graph are way more than just dots. They're actually clues. We are going to become shape detectives, using math to uncover the secret identities of all kinds of geometric figures.
So, what kind of story can a few simple points on a graph really tell? Well, it turns out they can tell you just about everything about a shape's size, its angles, and its real identity. From a basic circle all the way to a complex quadrilateral. The coordinates are the clues, and we're here to piece them all together. And to read that story, you just need the right set of tools. Seriously, think of it like a crime scene investigation, but for geometry. So we need to open up our detective kit and get familiar with the formulas that are going to help us crack these cases wide open.
Okay, let's jump right into Section 1, your geometric detective kit. These are the 3 fundamental tools we'll be using for every single investigation today. So here they are, the big 3. First, you've got the distance formula. We use this to measure the size of a shape's sides. Second, there's the slope formula, which is our go-to for figuring out angles and whether lines are parallel or perpendicular. And third, the midpoint formula, which is just perfect for finding the exact center of a line segment. Honestly, with just these 3, we can solve almost any case that comes our way. All right, let's warm up with our very first investigation, the case of the circle. This is a fantastic way to see how a single, simple formula can define an entire shape. And here it is, the circle's secret code. For any circle that's centered at the origin, its equation is always x squared plus y squared equals the radius squared. This simple little equation is basically the blueprint for every single point that lies on that circle. And check out how easy this is to apply. If we're told the radius is 7, we just pop that value into the formula. 7 squared is 49, so the equation is simply x squared plus y squared equals 49. Boom, case solved. But what if we don't know the radius? What if our only clue is a single point on the circle, say -5, 12? No problem. The circle's equation is tied directly to the distance formula. We can just plug those coordinates right in. -5 squared plus 12 squared, that gives us 25 plus 144, which equals 169. And that number, that's our r squared. We can even see how this works in the real world. Say a swimming pool has the equation x squared plus y squared equals 16. Well, we know that r squared is 16. That means the radius is just the square root of 16, which is 4 meters. And from there, we can figure out its circumference is about 25 meters. See? Cracking the code gives us actual, real-world answers. Okay, that was a good warm-up. Now let's see how this all builds into our next case, the triangle interrogation. This one's a bit more complex. We've got a shape defined by 3 vertices, and we need to figure out its true identity. So we have our 3 suspects, the vertices P, Q, and R. The first question we have to answer is this: is it a right triangle? To find out, we need to check for a 90-degree angle. And for that, we're going to pull out our slope tool. Okay, first things first, we gather the evidence. We calculate the slope of side PQ, and that comes out to 3/2. Then we calculate the slope of the side right next to it, QR, which is -2/3. Now we have the key pieces of information we need to move forward. And now for the crucial test. What happens when we multiply these 2 slopes together? Well, 3/2 times -2/3 equals -1. In coordinate geometry, getting a product of -1 is the absolute smoking gun. It proves, without a doubt, that these lines are perpendicular. They meet at a perfect 90-degree angle. And with that one definitive piece of evidence, we can state our first verdict. Triangle PQR is a confirmed right triangle, and that right angle is sitting right there at vertex Q. But hold on, the interrogation isn't over yet. Knowing it's a right triangle is great, but we can dig a little deeper. Our next question is it also an isosceles triangle? To figure that out, we need to check if 2 of its sides are equal in length. So it's time to switch tools and pull out our distance formula. Now we're going to measure the squared lengths of each side. This just helps us avoid dealing with a bunch of messy square roots. So the squared length of side PQ is 52. The squared length of QR is also 52. And the hypotenuse, that's the side opposite the right angle, PR squared is 104. But look at that. 2 sides have the exact same squared length. And you know what? That's all the evidence we need.
Since two sides are equal in length and it has a right angle, we can officially close this case. Our final verdict, PQR is an isosceles right triangle. All right, time for our toughest case yet. We're leveling up from a triangle to a four-sided figure, a quadrilateral. Let's see if we have what it takes to identify this shape as a rhombus. So, what makes a rhombus a rhombus? Well, the main thing is that all four of its sides are equal in length. So our first step is to pull out that distance formula again and calculate the squared length of all four sides, DE, EF, FG, and GD. And just look at the results. They all come out to exactly 10. That's some pretty strong evidence to start with. But hold on a second. Equal sides aren't quite enough proof on their own. I mean, a square also has four equal sides, right? To be absolutely sure this is a rhombus, we also need to prove that it's a parallelogram. And that means its opposite sides have to be parallel. And this is where our trusty slope tool comes back into play. We calculate the slopes of the opposite sides. The slope of DE is -1/3, and guess what? So is the slope of FG. That means they're parallel. Now for the other pair, the slope of EF is -3, and so is the slope of GD. They're parallel too. This is exactly what we needed to find.
So let's review the evidence, shall we? We've proven it has four sides of equal length, and we've proven it has two pairs of parallel opposite sides. This confirms every property of a rhombus. The verdict is in. This case is closed.
Okay, for our final act, we're not just identifying a shape. We're going to prove a fundamental geometric theorem. We're going to use our same detective kit to crack one of the hidden codes of all triangles. This is all about the midpoint theorem. Our mission, should we choose to accept it, is to prove that the line segment connecting the midpoints of two sides of a triangle is always parallel to the third side. So here's our game plan. Find the midpoints M and N, and then compare the slope of our new segment MN to the slope of the base, JL.
All right, first up, we're grabbing our midpoint tool. We find the midpoint M of the side JK by just averaging the x and y coordinates, and that gives us the point 2, 1. We do the exact same thing for side KL, and its midpoint N is located at 5, 2.
And now for the big reveal. We calculate the slope of our new segment MN, and it comes out to 1/3. Then we calculate the slope of the triangle's third side, the base, JL, and its slope is also 1/3. They are identical. And here's the crucial conclusion, the really cool part. Because the slopes are equal, the line segments MN and JL have to be parallel. Using our basic detective kit, we've just uncovered a universal rule of geometry. And this isn't just true for this one triangle, it's true for all triangles, everywhere.
And that brings our investigation to a close. We've seen how 3 simple formulas can uncover the true identity of shapes and even prove fundamental rules of the universe. It really makes you wonder, right? What other hidden codes are just out there, waiting to be cracked with a little bit of coordinate geometry?